In the last few segments, we began to investigate monosaccharides. Those are the individual units that join together to ultimately form complex carbohydrates. Some examples of so-called open-chain monosaccharides were these Aldohexoses shown here. We refer to them as Aldo because of the fact that they each have an aldehyde group here at the top end of the chain in the Fisher projection. We refer to them as hexoses because in each case, they have 6 carbon atoms. In the videos leading up to this, we limited our discussion mostly on these acyclic, also known as open chain, monosaccharides. In this video, what we're going to look at is the fact that in the body, these molecules exist in equilibrium with a cyclic form of the molecule. Shown here is this little cartoony illustration where we have not attempted to show the stereochemistry at any of the chiral centers through here because we have not shown any wedges or dashes or used any other special designation method to indicate the chirality at each of these 4 chiral centers within the cyclic molecule. This is important that these molecules exist in equilibrium between the cyclic form and the acyclic form because the cyclic form versus the acyclic form will have different ways in which they are recognized and processed by the body. We need to understand how this conversion occurs from one form to the other within the body, and that's what we're going to accomplish in this video. We will look at the reactions that transform monosaccharides, such as these Aldohexoses here, into the ring structure. So we're looking here at how we interconvert. By interconvert, we mean change from one to the other back and forth between the open chain and the cyclic monosaccharide form. Let's take a closer look. For this video, we will be focusing on a variety of different monosaccharides. Some of the common monosaccharides we see here in the image at the right. Some of these names you may recognize, some you may not, such as in the case of D-glucose, you very likely recognize that term. Some of the others that are less commonly known, such as D-idose, may be unfamiliar to you. You will notice we can break these into 2 different categories. We can break these into our category up here. All of these would be referred to as Aldohexoses because each of them have an aldehyde group shown here, and each of them have a total of 6 carbon atoms in their longest carbon chain. Here, 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 and here, making 6. Down toward the bottom of the screen, we have instead what we would refer to as Keto Hexos, going back to the designations that we learned and ways we learned to classify monosaccharides in an earlier video. We call these keto because of the fact that they have a ketone group, that's our carbonyl group, that's directly bonded to 2 carbon atoms rather than the carbonyl group being at the very end of the molecule, as was the case with the Aldohexoses. Keto hexoses, due to the fact that they have that term hexos in there, like Aldohexoses, have 6 carbons in that longest carbon chain. Hence, why we call them hexoses. We will focus our discussion here on the cyclization reactions that take place for these hexoses to form 6-membered rings as the product. Keep in mind that other carbon-numbered sugars, meaning pentoses, for example, can also form rings using a reaction completely analogous to what we will look at here. So let's go ahead and take a closer look at how we take these open chain monosaccharides and convert them into cyclic form. In order to understand how open chain monosaccharides get converted into their cyclic forms, we need to look back at a reaction that we learned in our aldehyde and ketone unit. That was the reaction where we took an aldehyde or ketone, we reacted with an alcohol, and we created a hemiacetal product. As a reminder, a hemiacetal product is a product where we have a single carbon atom that is directly part of an alcohol group, meaning it has to have a hydroxy group directly bonded, and it's also part of an ether group. I'll abbreviate that ether group as OR, and we'll define R here as an alkyl group. So in other words, it can't just be a hydrogen atom there. Otherwise, you would have a carbon atom that was part of two alcohol groups. So this has to be a carbon chain or carbon ring here. I will go ahead and additionally fill in to my structure R prime and R double prime, which would indicate additional carbon atoms that are linked to this central carbon. But what has to be present in the hemiacetal is it has to have the alcohol group directly bonded to the alkyl group. Now, in this reaction, we can sketch out our generic alcohol and aldehyde or ketone reactant to see how they relate to the hemiacetal product. Our alcohol reactant will be represented by the O alkyl group here is ultimately what the alcohol group becomes. So the alcohol group on the left side of the equation would be OR, and then the hydrogen there is what allows that to be an alcohol group. So during the course of the reaction, the O alkyl group from the alcohol, shown here in yellow highlighter, becomes the ether group of the hemiacetal product. The hydrogen, on the other hand, from the alcohol that I've highlighted in pink here in our alcohol reactant, that is lost during the course of the reaction. So when we are dissecting the relationship between the reactant and product in these reactions, the O alkyl group of the alcohol is what becomes the O alkyl group of the ether in the product. What about the rest of the molecule? Where does that come from? So the aldehyde or ketone we can sketch out a schematic of here as well. I'll draw in the carbonyl group that is essential to an aldehyde or a ketone. And then I'm going to draw in the R groups here, R double prime and R prime, and those would represent either hydrogen atoms or alkyl groups, depending on whether your starting structure is an aldehyde. If it's an aldehyde, one of those two has to be a hydrogen. If it's a ketone, both of those would be carbon atoms to make that a ketone functional group. And how this structure is going to relate to the final product, we can map out here. We have our carbons here, and potentially one of those could be a hydrogen atom, one of those R groups. That's going to come over here and relate to the product like so. And then the carbonyl group, which I will highlight here in gray, is what becomes the carbon that's directly bonded to the alcohol group in the final product. So now you might be looking at this schematic and saying, okay, that looks nice. Carbonyl group becomes an alcohol group. That same carbon atom right here is what becomes the hemiacetal carbon, because that's what picks up the O alkyl group. So it's this carbon atom right here that becomes the hemiacetal carbon in the product. But how does all this relate to forming a ring? Because nothing that I've shown here illustrates any rings. Well, if this reaction occurs intramolecularly, meaning that an alcohol group from one end of the molecule reacts with an aldehyde or ketone group from the other end, that reaction will yield a ring. So I'm going to go ahead and make a note here that the reaction when we're looking at making cyclic monosaccharides is an intramolecular reaction, meaning that there's an alcohol functional group and an aldehyde or ketone functional group in the same molecule, and those two groups within the same molecule, hence intra, meaning within the same, react with one another, and that reaction yields a ring. So intramolecular reactions yield hemiacetal rings. And that is indeed going to be the case with monosaccharides because of the fact that we have an abundance of alcohol functional groups present within monosaccharide molecules, as well as one aldehyde or ketone functional group. Now, you might be thinking about this and saying to yourself, well, there are multiple alcohol groups. How do I know which one will react to form a ring in this hemiacetal formation reaction? Well, what's going to be most favorable when looking at how these rings form, favorable reactions involve the formation of 5 and 6 membered rings preferentially. So 5 to 6 carbon rings preferred. And I should really say atoms here rather than 5 to 6 carbons, because technically not all of the atoms in the ring will be carbon atoms. One of them will be an oxygen, as we will see here. So the reason why 5 to 6 atom rings are preferred is because that enables the close to ideal bond angles. When we're looking at carbon atoms that have 4 groups bonded to them, those are sp3 carbons, and hence they have an ideal bond angle of 109.5 degrees. When the atoms are arranged into 5 to 6 membered rings, we see that bond angle that's ideal can be relatively closely approximated. On the other hand, if the ring size is smaller or larger, the molecule can't attain that ideal bond angle, and hence the reaction is less favorable. The ring is more difficult to form, in other words. And that's one reason why when we look at molecules in nature, it's very common to see 5 to 6 atom rings and less common to see rings that are larger or smaller than that. So let's take a look at how we can apply this general information toward looking at monosaccharides and their reaction. So I've zoomed out just a little bit, and I'm going to go ahead and look in here and draw the structure of glucose. I will go ahead and draw that as our Fisher projection for D-glucose. We could also be doing this exercise with the L-sugar. I'm not focusing on stereochemistry in this particular video. We'll look at that important topic of drawing the stereochemistry of the rings in the next video. But for now, I'm just drawing out D-glucose, and you could find this structure on the chart that we looked at earlier in this unit. Certainly, there's also a lot of resources online that would provide this structure for you as well. And you may have it memorized from some other coursework that you have taken. So here's the structure of D-glucose. We recognize it as the D isomer because D is determined by the orientation of this last chiral carbon. This is our final chiral carbon right here. And if the OH group on that carbon is on the right, that means it's the D configuration. And looking at D-glucose, we have several alcohol groups here, 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 and here. And we have an aldehyde group. So we have a situation set up here where we could potentially create a hemiacetal. And indeed, that's what we're going to do via an intramolecular reaction. So I'm going to go and draw in my equilibrium arrow here because this reaction works in both ways. The ring can break open to form the open chain monosaccharide. The open chain monosaccharide can go back this way to form the ring. It is a reversible reaction. And what's going to happen here, keeping in mind that we generally favor the formation of 5 to 6 atom rings, is that the same hydroxy group that determines whether the sugar is D or L is going to be the reactive one here to form a very favorable 6-membered ring. 6-membered rings are the most favorable ring size to form. And that's going to occur by having the lone pair electrons from that oxygen atom, which are electronegative, coming up and attacking the carbonyl carbon. To show that, I'm going to draw that carbonyl carbon out in a little more detail so that we can actually see the carbonyl group rather than just abbreviating it as CHO. So I'm drawing it like this. I'm going to put my lone pair electrons in so that we can make a map of what's going on here. And what's going on is that that negatively polarized oxygen atom from the same oxygen that is used to determine whether the sugar is D or L comes up, and it is negatively polarized. It doesn't have a full formal charge, but the electrons are unevenly shared, and this has the lion's share of those electrons, so it takes on a negative polarization. It's going to come up and attack the positively polarized carbonyl carbon. This carbonyl carbon is positively polarized because it's bonded to the electronegative oxygen. That electronegative oxygen is going to take the lion's share of the electron density from this bond, making that carbon positively polarized. And so we have a situation set up here where the oxygen atom is negatively polarized, carbon is positive, so they're very attracted to one another. And indeed, the oxygen atom is going to use its lone pair of electrons to come up and actually attack that carbon atom, forming a covalent bond. So when we say it's being attacked, what we mean is the oxygen is forcing the formation of a covalent bond there. In order for the carbon to avoid going over the octet rule, we take the electrons from the carbonyl group, specifically those pi electrons, and move those up onto the oxygen. That allows us to avoid going over the octet at this particular carbon atom. Now, this reaction is an intramolecular reaction because we have the OH group from one part of the molecule reacting with the carbonyl group of another part. And so ultimately this is going to yield a ring. let's map out what the ring will look like. In order to do that, I'm going to number the carbon atoms here. You can number these however you want. It doesn't necessarily have to follow with IUPAC numbering systems or anything like that. The way I've numbered this would, since we're starting at the aldehyde group, but it doesn't have to. We've just numbered these so that we can keep track of who goes where when we form our ring. So I'm going to begin in drawing my structure by thinking about how many atoms need to be in the ring. So if we imagine that looking through this molecule, our carbon atom here at position 1, 2, 3, 4, 5, those are all linked together. Position 5 is linked to this hydroxy group over here. And then, showing this electron pushing arrow to indicate the formation of a bond, we formed a bond back here to position 1. So what that results in is that we form a ring. And that ring is going to be composed of all of the atoms that are found here in this connected network that I've outlined with my kind of brownish yellow highlighter. Now count the number of atoms in total that are present within that system. So we have 5 carbon atoms. We come over with this oxygen, which is what is actually forming the bond back to here. So that's 6 atoms in total. Let's go ahead and draw a structure that has a 6-atom ring, a hexagon. 5 of those atoms will be carbons. 1 of those will be oxygen. So let's go ahead and draw that out. I'm going to go ahead and try to draw it color coding like we have the rest of the molecule. So position number 1 was originally our carbonyl group that I showed in green, so I'm going to show that in green here. Then I'm going to draw carbon atom 2, carbon atom 3, carbon atom 4, carbon atom 5. And then from 5 we had our oxygen atom that was bonded to a hydrogen. And that oxygen atom was what became bonded back to the carbonyl carbon of the aldehyde group. So this is our 6-membered ring. I'll go ahead and number this as well. Position 1, 2, 3, 4, 5. And then the OH group there was what we had in pink originally, so I'm just going to highlight it in pink there. And now taking a look at this and dissecting it, what we have is our skeleton. And I'm going to go ahead and fill in the remaining lone pair electrons and the remaining atoms to complete this structure. At position 1, paying close attention to what's bonded here, the details are an important aspect of this, and keeping organized and making your map is critical. So our carbon atom here was directly bonded to a hydrogen. Nothing has happened to that green hydrogen, so it's still bonded there, so I'm going to put that in as an H. Our carbonyl group, in order for this carbon to avoid going by the Tet rule, one of those pi bonds had to go up onto the oxygen. So I'm going to show the product of that, which would be our oxygen, which started with 2 sets of lone pairs to have its complete octet, now has instead 3 sets of lone pair electrons. I'll put the 3rd set in red there to emphasize that those originated from this pi bond right here that, using the electron pushing arrow, moved up onto the oxygen right here. And now going further through the system, because we've taken care of everything that's bonded directly at this carbon atom, because we had our hydrogen, hydrogen, oxygen, oxygen, and then the connection over here to the oxygen that allows the ring formation there shown in red. So with that in mind, we go to position 2. At position 2, there's an OH group directly bonded and an H in addition to the atoms of the ring. So I'm going to fill that in black here at position 2, OH and H. And we're not attempting here to show any stereochemistry, so it doesn't matter whether you put the OH here or the OH here. It's going to be the same structure one way or the other, because we're not trying to show stereochemistry. We're not using wedges and dashes or any other special designation. So I'm not worried about where the OH versus H goes. You could put OH here and H there again. Same thing at position number 3. I'm going to plug in OH and H. And again, I've put these in arbitrarily. You just have to have a hydrogen bonded somewhere to this carbon and an OH bonded to that carbon as well. That was position 3. Position 4 also gets an OH and H arbitrarily positioned, H and OH. At position 5, right here, things get a little dicier because we've got some more unique groups to bond here. At position 5, we have a hydrogen that we need to form a bond to. We also have this carbon was directly bonded to the OH group that swung around to form the ring. It's still bonded to that OH group here. Here was carbon number 5. Here's the OH group The OH group just looks a little different because it has that bond to the rest of the molecule there to make the ring. And then at position 5, in addition to the hydrogen, which we already drew in over here, we also have the CH2OH. That CH2OH is not part of the ring, so therefore we draw that in here like so, CH2OH. And now that we've done that, I'm going to go back to position 5, where we formed our ring. We took one of the sets of lone pairs to accomplish that. The other set of lone pairs, nothing happened to. Those are the ones that I'm highlighting right here on the reactant side. So those will still exist in our product, and I'm going to go ahead and plug those in. Now, if we calculated formal charges here, what we would find is that the oxygen atom up top here has gained electrons, and so it takes on a negative formal charge. You could use the formal charge calculation to confirm that that's the case. This oxygen has lost electrons because it started off with 2 sets of lone pairs. Now it only has 1 set, so it takes on a positive formal charge there. You could do the calculation of formal charge there as well. Now keep in mind it does have a complete octet, but the octet is not arranged in such a way that there is no formal charge. There is a formal charge there. So this particular molecule having formal charges on a couple of atoms is not the most effective, most efficient, lowest energy way of the final molecule looking. And so what happens in order to get to the final product of this is what we refer to as a proton transfer. I'm going to put proton as H plus transfer. What happens in a proton transfer is that a proton is lost from one position in the molecule and gained at the other in this particular proton transfer. So what happens is the oxygen atom that's negatively charged here is very attracted to this positively polarized hydrogen atom. So it comes over, grabs that hydrogen, that forces this hydrogen-oxygen bond to break so we don't go over the allowed valence of that hydrogen. The electrons go onto the oxygen here to give the final product of this reaction. So let's go ahead and draw that final product where the only difference between the structure that we drew in the intermediate and here is going to be the transfer of a single proton from one position in the molecule to another. So I'm drawing in all of my carbon atoms here and then filling in my hydrogens. I will try to color code here from here on. This carbon that was up top was originally the aldehyde carbon in our very starting material way back. It now is an OH group and has a hydrogen bonded to it as well. It became an OH because we had CO here in our intermediate that I'm highlighting. That CO picked up the hydrogen from here, so that's where it became COH. And I can highlight that particular hydrogen in pink there to color code it the same as the hydrogen that we had here. That's the origin where it came from. It was transferred from here over to here. So we have COH. Our oxygen atom here that originally had 1 set of lone pair electrons. Now we'll have 2 sets because when we broke that oxygen-hydrogen bond, we took the electrons from that reaction and those came over onto the oxygen. So that's why our oxygen final product has 2 sets of lone pair electrons. One I'll put in blue to reflect the color that was already here, and then the other I'll do in red because that was the electron pushing arrow showing that the electrons were coming over, so I'll do that in red. Coming through the rest of the system here at position 5, nothing has changed, so I'm just going to plug on to there a CH2OH and a hydrogen. At position number 4, at the very bottom of the molecule, we had an H and an OH, so I'm just going to redraw those. At position 3, we also had H and OH. At position 2, we had H and OH, so I'm going to draw those in. And again, since we're not showing stereochemistry in this particular video, it doesn't matter whether you put the OH here and the H here. As long as they're connected to the same carbon atom, you're in good shape there. And then at this point, we're back to position number 1. So looking at this final structure, we would describe this particular molecule as a hemiacetal because when we look at the structure of this, we can pick out that there is indeed a single carbon atom that is part of both an alcohol group and part of an ether group. So this particular carbon that I will put a big red star on, maybe 2 big red stars, is the hemiacetal carbon. And that's going to be important because when we start to look at the stereochemistry of sugars, there will be variability about how the two bonds are oriented here at this chiral center to give two different important forms of the sugar molecule in these hemiacetyls. So stay tuned for that. In the upcoming video, what we're going to do is take an additional look at creating these cyclic hemiacetyl sugars out of acyclic open chain starting materials, and we're going to look at the implications for stereochemistry, because certainly in D-glucose, the stereochemistry is critical to the biological effect of this molecule. And so we need to look at how that's going to play out when we get to the ring form as well. So stay tuned for that.